Since you're the only one here, got any specific problems we need to deal with?
I don't think so. I think the last test I didn't have my exam paper, my review document with me. I think that's what screwed me on that. Right now, I still have to sleep.
Yeah. Okay, so for your benefit, for the viewing audience benefit, this is a final exam for CHEM100. And I'm going to work from the review document, which is posted in Brightspace right now. And there's, in fact, the key is highlighted, so it shows you which ones we're going to do today. But I rechecked the school's final exam date and time for this class, and it's not Tuesday as in the schedule. In the syllabus, it's Thursday. So you have till Thursday nominally to do it, but I'm not going to fault you if you wait till Saturday night, because if you do it online, the system is going to grade it for me, so there won't be any delay. If you take it in person, then I'm going to grade it on the spot anyway, and that'll be Thursday. I'll be here. I won't be here Tuesday. Yes, it is. Yeah, I have to go vote. Primaries. Yeah, primary election day is on the 10th. Or you say, oh, is that Thursday?
One reason I asked is all I said Tuesday.
Yeah, Tuesday.
Because he said his work's off, but he's on call. So.
Yeah, Tuesday's the 10th. That's election day. So go vote in your primary. And Thursday, I'll be here for in-person exam, or I'll be zoomed in case you have any questions before you take the exam. And you can contact me any other time during my office hours, or text me, my cell phone, right? If you get in the heat of reviewing for the final and something just doesn't make sense anymore, give me a ring and we'll fix it. The other is a cautionary note. We're going to go over some problems today that are going to be like the ones on the final, but there may be subtle changes in the problems for the final. If you see one that looks familiar, don't assume that it's got the same answer. And if you've memorized the answer and check that one, it may very well be wrong. Okay, so learn how to work each of the problems. And then in the final, you'll be able to get the right answer following the procedure, not memorizing an answer. Okay, that's just the word of caution. All right. So let me get the magic wand. And this first page, we're going to do all of them. They're fairly fundamental and they'll go pretty quick. So for number one, water has a density of 1 gram per mil. 1.0 grams per mil. That's the density of water. Okay. Gotcha. See. You missed my introductory remarks. Number one, the exam is going to be on Thursday next week. That's the nominal exam date from the school. But if you're taking it online, you can go up to Saturdays, okay. And the other is, if you are in the habit of memorizing answers from the review document to take the exam, don't do that. Because the final exam may very well have changed parameters in that what looks like a familiar question. Learn how to work the question, and then with the information that's given, then you'll get the right answer. Okay, number one, density of water. So the question is, which one of these objects, 1, 2, or 3, will float? So we got these 3 objects, and we want to decide which one's going to float. Well, you have to understand Archimedes' principle, actually. What characteristic of an object will allow it to float? If the density of the object is less than the fluid that you place it in, then it will float. So we're really just calculating densities. And the density that's less than 1 will float the object. Okay? So for 1, we've got a mass of 50 grams and a volume of 69.4 mils. So the density of the first one is 50 grams and 69.4 milliliters. Now, you really don't need a calculator to answer this question. All you need to do is say, is that quotient greater than, equal to, or less than 1? And that's less than 1, yes. So this one will float. Then we can do each of the others. 60.9 grams divided by 54.7 milliliters. That's greater than 1. So that one will sink. And then the third one is 100 grams divided by 40 mils. That's much, much greater than 1. That will also sink. So that's why the answer is B. There's only 1 that will float. Ooh, kind of random eraser. Yeah, it's okay. Not best, but it works. Yeah, it worked out great. I think I'll use my rag and keep it falling on the floor. Okay, number 2. Number 2, which of the following describes a chemical property? A chemical property, remember, speaks to the substance's potential for chemical change. In other words, does it have anything to do with the identity change of the object? Right? So if we say gold is very dense, it's still gold, right? No change there. Gold is a soft metal. No change there. That's physical. Gold is an inert, non-reactive metal. That refers to its chemical nature. Right? It does not react. So it will not change to another substance under the most aggressive actions. And then the others, we found our answer. So the others should be physical also. Yellow metal, color, yeah. Good conductor of heat and electricity, that's physical. So really the only one that works is C. Right? That refers to a chemical property of that substance. All righty. Number 3. Stop that. Bounce around. Number 3. How many significant figures are in this number? Okay, remember your rules. You got non-zeros, and then you got zeros, and then the zeros come in 3 flavors. Zeros to the left, zeros in the middle, zeros to the right. So we've got zeros to the left, but they're bracketed by both a decimal and a non-zero number. Plus, if you have an explicit decimal, then everything to the right is significant. If we didn't have that decimal, then those zeros would not be significant. But since there is a decimal, you have 1, 2, 3, 4, 5. 5 significant figures. Okay, 4. Another significant figure question. 0.0040090. Okay, so we got all 3 types of zeros here. We've got zeros that are captured by non-zeros. We've got zeros to the right and zeros to the left. Zeros to the left are never significant. But if there's a decimal, then zeros to the right are significant. So that's 1, 2, 3, 4, 5. 5 significant figures in this number. All right, number 5. Which is an example of a homogeneous mixture. I think it's helpful if you're asked to match up any substance with a definition, is to look at the word structure. Homogeneous and mixture. The way the English language is structured, it's best to start from the end, work backwards. So which of these are actually mixtures? Well, soil is a mixture. Sodium chloride is not a mixture. It's a compound, so it's a pure substance. Aluminum is an element. It's not a mixture. Vodka is a mixture of water, ethanol, and some other stuff. Oily water, that's a mixture. It's 2 different substances, and in a mixture, each of the substances that are combined, 2 or more substances, must retain their identity. So we have soil is a mixture, vodka is a mixture, and oily water is a mixture. Now, which ones are homogeneous? Yeah, vodka is homogeneous. Soil is not, it's heterogeneous. Oily water is heterogeneous. And what do we mean by that? We mean that its composition is uniform throughout. Exactly the same amount of each of the substances in the mixture, percentage-wise, is the same no matter where you sample. And vodka is the only one that works there. What's another name for homogeneous mixture? Solution. Solution and homogeneous mixture are synonymous. Okay, so the answer is vodka. All right. Oh, by the way, there's a very good chance that I'm not going to be able to finish this in 2 hours. So if you have to go ahead. I'll keep recording and finish all the highlighted ones that I've marked. Okay, and you can go back and pick up where we left off if you have to go. All right, so let's see. I got to go over here and scroll down a little bit. Pick up 2 of them. Yeah, there we go. 6. Cat is 7.1 pounds. That's about average size for a cat. I don't know. Most of my cats are bigger than that. But the question is, what's the mass of the cat in kilograms? This is simply a unit conversion. So if you have 7.1 pound and you want to convert it to kilograms, you need a conversion factor that will leave you with kilograms, which has to go on top, and cancels pounds. So we need a conversion factor. And anytime you have an equivalence, you automatically have a conversion factor. 1 pound is 2.2046 kilograms. Right? So if we do the math and we keep only 2 significant figures, then we should get 3.2 kilograms.
It's 2.06 pounds per kilo.
Oh, you are absolutely right. That shows somebody's paying attention, not the instructor. There you go.
Otherwise, I was 14 something.
Right, yeah, that's right. Estimation to check yourself, right? I should have done that. I would have seen that right away. Okay, that was 6. Eight. Which of these is a chemical property? Okay. Same line of reasoning as the gold before. So we need something that speaks to the identity of the substance. Ice melts, now it's physical. Water has specific heat, that's physical. Sodium is a soft, shiny metal. Now that's physical property. Helium is very non-reactive. That's the one. Helium is non-reactive. Glycerol is a viscous liquid. That's true, but it's not chemical. Okay. Let's see, number 10. Looks like another unit conversion. Let's see if I can get this one right. 45.5 K. 485. K is what in degrees Fahrenheit or Celsius? We have several choices. Notice. So, what I would do first is convert it to Celsius and see if any of those match Celsius. So in order to do that, we have to subtract 273, right? So that would be 2, 1, 2, 212. So is there one of those? Well, the number's right, but the units are wrong. This one's right. Here we go. 212.5 C. Now, if none of those Celsius had been correct, we would have had to taken this and convert it to Fahrenheit with our formula. And then we could compare the Fahrenheits and found the answer. But in this case, we got the answer. I think it's my marker. It's my marker that's difficult. All right. Let's see. Oh, here. Let's scroll up. Maybe we can get both of them. There we go. 14. Which of the following is only a physical change? Let's see. Leaves turn color in the fall. You have to understand a little bit about biology. The change in color is physical property, but they change in color because they're undergoing chemical change. So A is a mixture of chemical and physical. A banana ripens. That's chemical. It's biochemical. Actually. Yeah, it's biochemical. Cookies burn in the oven. That's a chemical change. Right? You're converting the primarily starches and proteins into carbon. Sugar dissolves in coffee. That is purely a physical change because you've got sugar before, you got coffee before, you got sugar after and coffee after. Only now they're in the mixture. So D is the answer. Not at least 2 of the above, but just D is only a physical change. 16. If a 100-gram sample of a metal has a volume of 8.65 milliliters, what's the density? Right. This is simple calculation. Density is mass divided by volume. We have 100 grams divided by what volume? 8.65 milliliters. And we check the units. all the answers are in grams per milliliter, so we're good there. We just do the calculation and we should end up with 11.6 grams per milliliter with 3 significant figures. That one's got 4, this one's got 3, so that one has 3. And that seems reasonable. Ready. 17. 14.809 rounded 3 significant figures. All right, 3 significant figures, count from the left. 1, 2, 3. So we're looking at this one to determine what to do with that one. So when this one goes away, that one's less than 5. So that's all that's left, 14.8. 18. Which of the following is an incorrect description? Okay, we're gonna have to look at each one of these now. Okay, homogeneous mixture. Are those terms compatible? Yeah. You can have a mixture and it can either be homogeneous or heterogeneous. So A is valid. A solid element. Oh yeah, we got lots of them. Most of the left-hand side of the periodic table is solid. How about a solution of gases? Yeah, gases, in fact, 2 or more gases together always make a homogeneous mixture, a solution. So C is also a valid statement. A mixture of solids. Yeah, think alloys, like brass, nickel and copper, or steel. It's a mixture of carbon and iron and other stuff too. So by process of elimination, E should be wrong. A heterogeneous compound.
Sounds weird.
Yeah, it should sound weird. A compound is a pure substance. It cannot be described in terms of mixture. Okay, so E's wrong. Let's see here. 20. The state of matter for an object that has neither definite shape nor definite body. And we're only looking at 3 types of phases of matter: solid, liquid, and gas. Right? So we can refer to them in terms of their shape and their body. Right? Solid has a definite and a definite shape and body. Liquid has an indefinite shape, but a definite body. And gas is indefinite and indefinite. So since they have neither definite shape nor definite volume, it has to be a gas. All right. Oops, I have to scroll this one. Here. It's good. 24. How many of the following are pure compounds? Oh, sodium, sugar, oxygen, air, and iron. Sodium, sugar, oxygen, air, and iron. How many of these are pure compounds? Okay, English language again, work backwards. Which are compounds? That's not a compound, that's an element. That's not a compound, that's an element. That's an element. So Which ones of these are compounds? Sugar's a compound. Is air a compound? No, it's a mixture. It's a mixture. So by process of elimination, sugar should also be a pure compound, and it is. Because when you have sugar in your possession, it's only sugar and nothing else. That's pure. All right. 26. Oh, now that got highlighted. We're still recording. Which of the following is a chemical change? A chemical change describes a change in identity of a substance. So when we look at sugar dissolving in water, you still got sugar, you still got water, no chemical change there. Gasoline evaporates, simply changes phase from liquid to gas. Water boiling, liquid to gas change, physical change. Paper burning, yep, you're changing primarily cellulose into carbon dioxide and water and some leftover ash, maybe some unburned carbon. So D is a chemical change. Melting butter has a phase change. All right, 28. What's the most abundant element on Earth? Oxygen. Yep. It's in your, let's see. I looked that up a little while ago. I think the 9th edition is about page 74, 73, table 4.1, in case you're interested in any of the other elements. But oxygen is the most abundant. Oxygen, most abundant in the Earth's crust, oceans, and atmosphere. While we're on the topic, how about the human body? Oxygen also, right? Why would you think that? Now this is by mass. Well, for the same reason that it's the most abundant one on the Earth's surface. Oceans, H2O, lots of oxygen. There's probably more hydrogen by number of atoms, but by mass, oxygen outweighs, simply because there's so much water. They don't call this the water planet for nothing. The correct name for this third, FeO. All right, so what do we got here? Type 1, type 2, type 3. Well, yeah, type 2. It's definitely not a type 3 because there's a metal nonmetal. So it's a toss up between 1 and 2. And since iron can have more than one possible charge, it has to be type 2. And that means you have to say what the charge is. So we would say iron 2 oxide. And we're working from the fact that oxygen is -2 charge when it's in an ionic compound like this. So that means this one has to be +2. Okay. All right. Let's see. When the following equation is balanced using the smallest possible integers, what's the number in front of the substance in bold? And if it's not showing up too well, the bold one is iron. So 32. And we've got aluminum, Fe3O4, I believe. And then aluminum oxide, and I started too far over. My bad. Come over here. Man, gives us more room. And then iron. So we want to know what's the coefficient in front of iron. Well, remember what we do. If there are three elements, we save those to last. Right? You can set up a budget if you want, but this one's pretty simple. What you notice is that if we're going to balance iron, we have no problem balancing iron. Right? If we get a coefficient in front of this one and this one, we can balance iron and aluminum independently. So we focus on this one and we focus on the oxygens. Notice that one oxygen is 3 and the other one's 4. Right? The best way to balance those is to cross multiply. So we'll take this 4 over here and this 3 over here. And that gives you 12 oxygens. We're good. So now we have 9 irons and 8 aluminums. But there's our answer. Any golfers in the group? No? Ever hit a 9 iron? I guess not. It's designed to make the ball go way high and short. Okay. So the answer to 32 is D, 9. Let's see, 33. I'm going to have to scroll that one a little bit to get it all. Let's get that one too. All right. 33. A gas sample 30.3 liters at 2 atmosphere pressure and 27 degrees Celsius. How many moles of gas are present in the sample? This is a gas problem where you have to decide, is it a before and after or a state? That will determine what type of formula you need to use. We don't know how it got there. We're just given those values for the gas. So this is a state situation. And to answer this question, we use the ideal gas equation. Okay, so I like to extract things from problems. We've got a volume of 30.3 liters. We've got pressure of 2 atmospheres. We've got a temperature of 27 degrees C. We know we're going to need K, so we might as well do it now. And the question is, how many moles is that? So we're working from this equation, and we're going to solve for moles. So that's PV over RT. So pressure, and when you're using this equation, remember, you've got to have the right units. The units have to match the units that are found in that constant. So pressure, 2 atmospheres, that's good. Volume needs to be in liters, 30.3 liters, divided by the gas constant, 0.08206 liter atmospheres per mole K, and temperature, 300 K. And if we do the calculations and we are restricted to 3 significant figures, you should come out with 2.46 moles. In this case, the only unit we had to change was temperature. The rest of them were kosher by the gas constant units. And this should be on the last useful information, right? That value. Right? So you don't have to have it memorized. If you've done enough problems, you've already got it memorized, so. Let's carry on. Use this thing, see if it works here. It's not doing too bad now. Just have a few specks here and there. 34. You're holding 4 balloons, each contain 6 grams of a different gas. The balloon containing which gas is the largest? So conditions for the problem are buried in the answers. You have nitrogen, helium, potassium, and neon. I bet that was supposed to be krypton. You can have potassium gas. You just got to get it hot enough. But I'm thinking that needs to be krypton. I want to make myself a note. It would go over better if it were krypton. Okay, let's assume that they're all gases anyway. So if there's 6 grams of each one of them, 4 balloons, each containing 6 grams, the balloon containing which one is largest? So we're allowing the volume to change. The volume can change, right? Remember, to describe a gas, we need those 4 conditions. Temperature is constant. Pressure is constant. These two vary, volume and moles. That means we're dealing with Avogadro's law, which means that volume divided by moles is a constant. So if we allow the moles to go up, the volume goes up. But we're told that there's 6 grams of each one. Right? So what effect does that have on volume or moles? Well, volume is a response. It has an effect on moles because each gas has a different molar mass. So how do you get, but we're aiming for which is the largest in volume. So what does that mean? That means which one has the most moles, right? The one that has the most moles has the most volume because these are directly proportional. So which one would have the most moles? If they're all the same mass, it would be the gas that has the smallest molar mass, which is the smallest molecule or atom in the group, because it takes more of them to make 6 grams. And that would be the lightest one, helium. 6 grams of helium would have many more moles than any of the others. Okay? Get the reasoning there? That's 34. Let's see. 38. Now 38 looks like a big problem. There's lots of words there. What you got to do is pick out the information that you need to answer the question. So what's the question? Determine the partial pressure of hydrogen gas in the mixture. Okay, we got a mixture. What's the mixture? Mixture is zinc metal is reacted with hydrochloric acid, right? When that happens, it produces those two, like that. It produces this gas. And we're collecting that gas over a liquid, probably water. And what we're saying is that when we collect that gas, we want to know what is the partial pressure of the hydrogen gas without the vapor? Right? So what we've got here is a Dalton's partial pressure problem. So the total pressure, let's see. Yeah, the total pressure is going to be equal to the pressure of hydrogen plus the pressure of, let's just assume it's water vapor. Okay, so are we given enough information to answer that question? Well, we're given a lot of extraneous values, right? We're told the temperature, but we're also told the partial pressure, so we didn't need temperature. Partial pressure of the vapor here is 18 torr. Okay, we're also told the volume. We don't need the volume. We need the pressure. So the total pressure is 0.508 atmospheres. Okay, so at this point, we can calculate this if we resolve the unit difference. Okay, so how many torr is 0.508 atmospheres? Well, we need to convert it. Atmospheres on the bottom, torr on the top. 1 atmosphere is 760 torr. So 760 times 0.508. Is 386. 386 torr is the total. So if we subtract 18 from that, we're going to get that value. $368. Okay, that's why the answer is D. Okay, so there was a lot of blue smoke in that problem. That's why extracting information and putting it in a separate location is the way to keep from being confused. Okay, 39. Solid carbon dioxide is placed in a Ziploc bag. Solid carbon dioxide sublimes, that turns directly into gas from a solid at a rate of 0.726 grams per minute. If the pressure builds to 3.75 atmospheres at a temperature of 21.1 degrees Celsius, what is the final volume of the bag after 4.97 minutes? Okay. So let's say, what are we given? Put it all on the board separate. 0.726 grams per minute is the sublimation rate. The final pressure is 3.75 atmospheres. Okay. Temperature is 21.1 degrees Celsius. Question is, what's the final volume? Well, we're also given time, 4.97 minutes. So time equals 4.97 minutes. One other factor. Or is that enough? That's all we're given. Question is the volume. Okay. So one thing should pop out here. If we're trying to find the volume, then we could possibly use the ideal gas equation. Right? Solve for mole, solve for volume if we had moles. So how do we find moles? Moles is also a question. If we want to use the ideal gas equation. So if we're going to go for moles, we need to know how much carbon dioxide is in that Ziploc bag. Well, we've got time and we've got rate, so we can find out how the mass of CO2. Right, we could say, well, let's just do it like this. Multiply that times time, 4.97 minutes. Right, and that will give us the mass of CO2. So 3.608 grams. So we get 3.608 grams of carbon dioxide. Now that we know the identity of the gas and we know its mass, we can find the moles. What we need is molar mass. So what's the molar mass of carbon dioxide? Well, let's see. 2 oxygens is 32, and 1 carbon is 12.01. So that's 44.01. Okay, so if we divide that into 3.608, we get 8.199. 8.199 times 10 to the minus 2 moles. Now we got moles. We got moles, we got temperature, we got pressure. We can find volume. So solve for volume. There. Let's see, we're going to need Kelvin here. All right, so volume is going to be moles, 8.199 times 10 to the minus 2 moles. I'm going to leave out the units just for space. 0.08206. And temperature. So the temperature is going to be what? 294.1. Kelvin divided by pressure. Pressure is 3.75 pascals. Okay, so now we have to do is crunch some numbers. 0.08206 times that value. 294. That one and divided by 2.7. So I get a point. Let's see. I can keep 3 significant figures, I believe. 0.528. 0.528 liters. Our answers are in milliliters. So we got to convert to milliliters. 528 milliliters. There we go. That's B. Okay. Let's see here. I might scroll that one. That's good. 41. You're holding 2 balloons of the same volume. Okay. So volume 1 equals volume 2. All right. 1 balloon contains 1.05 grams of helium. 1.05 grams. This is helium. The other contains neon. Okay, what's the mass of this one? Well, we don't have any laws that relate volume and mass directly. What we have is a relationship of volume and moles. So if you have equal volumes, what does that say about the moles? All right, exactly equal. So the moles here of helium equal the moles of neon. Okay? So if we have exactly the same number of moles, then the ratio between the two that tells you the mass difference is molar mass ratio. So if you ratio the molar mass of neon to helium, we can find out what the ratio of moles is. Right? And neon is 20.18 grams per mole. And helium is 4.00 grams per mole. So the ratio there is about 5. It's a little more than 5. 20.18. 5.05. 5.05 is the ratio of the two. So if they have the same number of moles, their masses should be different by that factor. 5.05 times 1.05. Is 5.30 grams for neon. Close. So here's a case where you pick the best answer. The best answer is A.
Sorry, I'm okay with that one.
That fall asleep. Yeah. Okay, pick it up. I'll just keep rambling on. Careful driving.
Yeah, so I'm gonna go ahead and get in here.
All right, 41 and 44. A gas occupies 42.6 liters at 2 atmospheres pressure and 27 degrees C. What's its volume? If the pressure is decreased to 1 atmosphere at constant temperature. So let's put what we know up here. Our starting condition, 42.6 liters. And starting pressure equals 2 atmospheres. And temperature, 27 degrees C. And we're looking for the volume. What conditions are changed? If the pressure is decreased to 1 atmosphere and the temperature is constant. So the temperature is the same as it was before, right? We don't have to consider that one. Temperature is constant. So what we're seeing is pressure volume variability. That's Boyle's law. So Boyle's law says this. And we're going to solve for that one. So V2 equals P1 V1 over P2. Right? So this is 2 atmospheres at 42.6 liters. And then pressure final is 1 atmosphere. So we're actually multiplying 42.6 times 2, which should be 85.2. Yeah, 85.2 liters. That's B. $45. Okay. There's a lot of words here. You have a partially filled party balloon with 2 grams of helium gas. So we've got a partially filled party balloon with 2 grams of helium. Okay. Then add 3 grams of hydrogen. We're going to add 3 grams of hydrogen to that. Constant temperature and pressure. Pressure and temperature are constant. All right, that's good. How many times bigger is the party balloon? Comparing before and after hydrogen gas has been added. Well, actually, the question is not how many times bigger. The question is, what formula do you use to calculate that? What's the best formula to use to solve this problem? Well, what are we dealing with here? If pressure and temperature are constant, then what other 2 factors do we consider? Volume and moles. Volume and moles means Avogadro. So Avogadro says before is equal to after. Right? And we've changed this value here from this one to that one. So all we have to do is, we actually want to answer the question, is, well, it doesn't give us the starting volume, so we have to do it theoretically. Right? You're going from this volume to the new volume after adding so many moles of hydrogen to so many moles of helium. That's the best formula to use. And that's why the answer is this one right here. $45. Let's see here. 46. A gas occupies 18.5 liters at STP. Volume equals 18.5 liters. Standard temperature and pressure. Standard temperature is 0 degrees Celsius, and pressure is 1 atmosphere. Okay. What volume will it occupy at 735 torr? So this is beginning 735 torr is the final pressure, and the temperature is raised to 57 degrees. Temperature to 57 degrees Celsius. So let's see, we've got temperature, pressure, volume. That's the question. What volume will it occupy? Right. This is a before and after situation. But we also have to reconcile units of measure. Temperature always has to be converted. Right. So this is 273 K, and this is, let's see, 0, 3, 330 K. How about pressure? Pressure and volume, you can pick your units as long as they're the same. So I think it would be easier to say, instead of calculating atmospheres here, you say 1 atmosphere is equal to 760 torr. Okay, now we can solve using the combined gas law. So P1 V1 over T1 equals P2 V2 over T2. All right. So we're going to solve for V2. V2 then is equal to P1 V1 T2. And then on the bottom over here, P2 comes over P2 T1. Okay, now we just have to plug in the numbers. Right. 760 torr, volume 1, 18.5 liters, and T2, 330 K. Then on the bottom, second pressure, 735, and T1 is 273. Right. If you calculate that out, you should get 23.1. liters. In the interest of time, I didn't bother to calculate it myself. All right, that was 46. All right, let's scroll 48. I need to down here. Ooh, got 3 of them. Can I get them all? Nope. Can't get them all. I messed up. Quicker to come back over here. 48. Let's do it like this. There we go. 48. All right, identify the Bronsted acids and bases in the following equation. A stands for acid, B stands for base. All right, so our equation is HSO3 minus plus CN, that minus should be up there, yields HCN plus SO3 2 minus. Okay. Bronsted, Lowry-Bronsted acid bases. A Bronsted acid donates a proton. A base receives or accepts the proton, 1 proton at a time. So which one gives up a proton over here? That one. That makes this the base. It receives. So when it gets over here, now we have a conjugate acid and a conjugate base. Okay? AB is B. (49). Which has the higher hydrogen ion concentration in solution, obviously, between these two solutions, 0.4 molar rubidium hydroxide and 0.2 molar calcium hydroxide. Well, remember, in a solution, this reaction is always going on. Right? And the K value for this, actually, it's got a special subscript there, is 10 to the minus 14. So whenever you know one of them, you can calculate the other one. Which means if we have a solution comparing 2 solutions, if the concentration of hydroxide is the same in both of them, then the hydrogen ion also must be the same. Or if we know what these are, we can calculate the hydrogen ions and compare them. So let's find out from these 2 solutions, what is their hydroxide ion concentration? And these are both strong bases. So if we're given a concentration of each one, we know that that concentration will generate a hydroxide ion concentration for us. So 0.4 molar rubidium hydroxide equals what? 0.4 molar hydroxide ions. 0.2 molar calcium hydroxide yields what concentration of hydroxides? Well, for each one of these, you get 2 hydroxides. So the hydroxide concentration is twice that value. Okay? The hydroxide ion concentration for both of these solutions exactly equal, which means the hydrogen ion concentration of each one is also equal. That's why the answer is D, hydrogen ion concentrations are equal. Which has the higher one? Neither. Neither one has the higher. They're exactly equal. All right, then. 50. Calculate the pH of an acid solution containing 0.044 molar HNO3. What do we know about HNO3? It's a strong acid. So if we know the concentration of the acid, we also know the concentration of the hydrogen ions. This is 0.044 molar hydrogen ion. So how do we calculate pH? Negative log of the hydrogen ion concentration, which would be equal to negative log of 0.044 molar. And if we run the numbers, take the log of this, change the sign, we get 1.36. So is that an acidic solution? Oh yeah, very acidic. It's much, much smaller than 7. 7 is neutral. Anything less than 7 is acidic. Anything greater than 7 is basic. All right, that was 50. 51. Which of the following statements are correct? So notice we have all of the above are correct or none of the above are correct. So we got to look at each one, A through C. What about A? In a neutral solution, those values are equal. Is that true? Yes, it is. That's a true statement. This is a neutral solution. B, in an acidic solution, hydrogen ions are greater than hydroxyls. Is that true? Yep, that one's true, that one's true. How about C? In a basic solution, that's greater than that. Is that true? Yep. So they're all true. That's why D is the answer. Now 52. Let's see, calculate the hydrogen ion concentration in a solution that has a pH of 5.15. So if the pH is 5.15, what does that mean? This is a mathematical manipulation. That's equal to negative log of the hydrogen ion concentration. And the question is, what is that value? So how do we do that? Well, we take the negative sign over here, right? And that's equal to this one. Then we resolve the log function, which means what? A log means this is base 10. That value is that value to this power. So that means this is equal to 10 to the minus 5.15. Right? On your calculator, that's what you do. Change the sign and 10 to the x key will give you the answer. This is also called the anti-log. Right? So that's the anti-log of the negative value of the pH. Okay, and the value should come out to 7.1 times 10 to the minus 6 molar. Notice significant figures. The number of decimal points in that pH is equal to the significant figures in the hydrogen ion concentration. So we've got 2 decimals, we have 2 significant figures. That's the way that works. All right. Okay, gotta scroll down 53. A solution where hydrogen ion concentration is equal to 10 to the minus 13 molar. Okay, is either acidic, neutral, or basic, or strongly acidic. Right? So we know that pH equal to 7 is neutral, right? So what is the pH of this? Right? Negative log of that value is 13. It's easier to wrap my brain around it when I look at it this way. That means it's greater than 7. This is basic. There you go. It's a basic solution. All right, 58. Oops. I always forget to do this. There we go. My battery was going low on me. Knocked it out of alignment here. There we go. All right. So back to the problem. Choose the pair of compounds with the same empirical formula. Right. So what's the empirical formula? It's the simplest whole number ratio of elements in a compound. So what you have to do is look at these 2 in each of the groups and say, is one a simplified version of the other? H2O and H2O2. All right? No. How about this one? C2H2 and C6H6. Yep. That's a good one. So how would we get from this one to that one? Multiply each one of these by 3. And that will give you C6H6. This is the empirical formula. Actually, the empirical formula of each one of these is CH. For this one, X equals, do like that, X equals 2. For this one, X equals 6. So the empirical formula of these 2 compounds is CH. If we look at the others, right, we cannot reduce these to an empirical formula because that was 4 and this was 7. This one cannot be reduced either. None of these can be reduced to the same empirical formula. The only one is B. All right. 60. Let me see if I can do this without messing it up. Over here, like this. Oh, went too far. Let's see. Yeah, now I'm going to settle on this one. 60. Acetylene gas is 92. Acetylene gas is 92.3% carbon 92.3% carbon, 7.7% hydrogen. Okay, by mass. And its molar mass is 26 grams per milliliter. So the molar mass is 26 grams per mole, excuse me, not milliliter, per mole. Okay. What is the molecular formula? All right, to solve this one, we've got to do the empirical formula and then make the conversion to the molecular formula using the molar mass. So remember what we do when we have percentage by mass? You can't convert these to moles, and the compound, the elements in the compound are related by numbers, not by mass. So we got to convert to moles. So if we've got 92.3 parts per 100, why don't we just say the 100 is 100 grams? Right? In 100 grams, you've got 92.3 grams of carbon and 7.7 grams of hydrogen. Now we can convert to moles. Right? Henry Ford's coming along here. All right, so hydrogen is 1.01 gram per mole. Carbon is 12.01 grams per mole. So we just calculate 92.3 divided by 12.01. And that's 7.69. 7.69 moles in a 100 gram sample. 7.7, 1.01 is 7.62. 7.62 moles. Okay. When we get to this stage, rounding is permissible. And estimation even. These are very close to one another. Right? Normally what we would do is take the smaller one and divide everything through by that one. This is the mole ratio of carbon and hydrogen in acetylene. But they're so close together, calculation, experimental error would make this approximately 1:1. So that means CH is the empirical formula for acetylene. What we needed to do is determine what the multiplier is. Right? So how do you do that? Well, you find out what's the molar mass of this formula. 12.01 plus 1.01, right? So it'll be 13.02. That's the empirical mass, grams per mole. If we have a multiplier here, then it gives us this value. Okay? So 26 grams per mole divided by 13.02 is equal to X. That's the multiplier. And we're going to estimate again because we need whole numbers. So a whole number ratio here is 2. That means the formula is C2H2. Okay? Now, if you're given a different set of data here, carbon and hydrogen, then you need to go through this procedure. You don't just assume that it's acetylene and the answer is going to be that one. If you do, you probably get it wrong. You need to do the calculations step by step. All right, 61. You've got 1 mole of each compound below. Which has the greatest mass? All right, if there's a mole of each one, and you know the molar mass of each one, then you know the mass of a mole. So by calculating the molar mass, we can compare those values, and that would tell us which has the greater mass. Sodium hydroxide. The key to this one is to knowing how to write the compounds. Because if you can't write the compounds, you cannot calculate the molar mass. Sodium hydroxide. Barium carbonate. Barium is an alkaline earth, right? It has a 2+ charge. But carbonate is a polyatomic ion with a 2+ charge, right? So they balance one of each. Iron 3 sulfate. We have iron and sulfate. If this is a polyatomic with 2- and this one's 3+, right? Because of that right there, then we need to cross. This is a 2 and this is a 3. Ammonium nitrate. Ammonium nitrate. -1 +1. That's all you need. And the last one, lead 4 oxide. So lead has a 4+, and oxygen has a 2-, which means we need 2 of these. So there are your formulas. We need to calculate the molar mass of each one of these. All right. So sodium is 23 plus 16 for oxygen plus 1.01 for hydrogen. That's 40.01. 40.01 grams per mole. How about barium carbonate? Barium is 137.33 plus carbon plus 3 oxygens. 3 times 16 is 48. Okay, so 48, 12.01, and 137.33 is 197.34 grams per mole. 2 irons, 55.85. 2 times 55.85 plus 3 times sulfur. So that would be 3207. Plus 12 times oxygen. Right, so let's do some fancy calculator work here. All right, and then 32.07 times 3, and then 12, enter 16. 399.94. Did I do that right? Let me do that. I think I hit the key wrong. Oh, that's right. So far, C is the winner. How about this one? 2 nitrogens, which would be 28.02, 4 hydrogens, 4.04, and 3 oxygens, 48. I think we're pretty safe there that that's going to be less than the one we've got above. Yeah, 80.06. And the last one, lead. 207.21. 207.21, and 2 oxygens are 32. $239.21. There we go. So this one right here is the heaviest. 1 mole of each. That's how much 1 mole would weigh of that compound. So here you have iron 3 sulfate, And the only reason we can say that is because we know how to write the formula. That's the kicker for this one. If you can't write the formula, skip the problem. You'll never get it right. All right, 63. A certain compound has an empirical formula of NH2O. NH2O. Empirical formula. Its molar mass is between 55 and 65. So they're saying that this one produces a molar mass between 55 and 65 grams per mole. All right. So what we need to do is find out how much does this one weigh, the empirical weight. So nitrogen is 14.01, we just write it here, 14.01, 2 hydrogens and 1 oxygen. We add those together. And that's 3203 grams per mole. So what we need to do is to ratio this one to that one. Right? So if we say if X is 1, if X equals 1, then the molar mass is equal to 32.03, right? That's too small. If X equals 2, the molar mass is 64.06. Bingo. So X equals 2, that means N2H4O2 is our formula. Right there. Okay? All right, 64. What's the molar mass of lithium sulfate? This one should be fairly straightforward. Use your periodic table. Lithium, 6.94. 2 times 6.94. Then 1 sulfur, 3207. And 4 oxygens. Here we go. So 64 oxygens, 32.7, and 6.94. I get 109.95 grams per mole. All right. Closest one to that is B. That's the best answer. What we have here is rounding error. My guess is that they used 16, maybe only 32 for this one. Two lithium, 1 sulfur, 4. Okay, that's your answer. 64. Let's see here. 71. Yep, that's everything. We can get 71 there. Convert 0.205 mole of calcium hydroxide to grams of calcium hydroxide. This is conversion factor time. Moles on the bottom, grams on the top. All right, so how do we calculate that? We use the formula. calcium is 40.08. 2 oxygens, 2 hydrogens. Right, so 40.08, 32, 2.02, 74.10. There, times 0.205 is 15.2, rounded off to the nearest 3 significant figures. 15.2, right there. All right, let's see. Skip a few. Let's see if I can do this without messing up. Right there. There we go. I'm gonna leave it at that. 78. When 10 moles of calcium metal is reacted with 3.9 moles of oxygen gas, how much calcium oxide is produced? And the answers tell you that you only need to convert moles. So in order to answer this one, this is a stoichiometry problem. You need to be able to write the balanced equation. Calcium metal plus oxygen gas yields calcium oxide. That's also a solid. All right, oxygen is a -2, calcium is a 2+, so 1 of each is all you need. So now we've written out the correct diatomic, don't forget that. So we need 2 oxygens over here. And we need 2 calciums. So there's your balanced equation. Got to have a balanced equation or you can't do the problem. Now what do you get? 10 moles of calcium metal reacted with 3.9 moles of oxygen. How many moles of calcium oxide? At this point, it's a stoichiometry problem, but it's also a limiting reactant problem. You're given exactly these amounts of calcium and oxygen, which means one of them is going to run out. So which one runs out? If you use your conversion factor, this is calcium, convert it to calcium oxide. Right? 2 and 2. That's 10 moles of calcium oxide. If all of the calcium is consumed. What if all of the oxygen is consumed? 3.9 moles of oxygen. Calcium on the bottom. Oh, excuse me. Oxygen on the bottom. Calcium oxide on the top. You have a 2 here, the calcium oxide, and a 1 there. So 2 times 3.9 is what? 7.8? 7.8 moles calcium oxide. So the one that runs out first is oxygen, and it can only produce that much. So that's why the answer is 7.8 moles, not 10 moles. All right. Okay. Oh, 81. Let's see. Let's go over here. There we go. 81. for the reaction, sulfur plus oxygen yields sulfur trioxide. How many moles of sulfur trioxide can be produced from 7.2 grams of oxygen and excess sulfur? So in this case, you don't have, well, the limiting reactant is oxygen because you have plenty of sulfur. So the equation's already balanced for you. All right. So what do we get? 7.2 grams of oxygen. And excess here. So the question is, how many moles of sulfur trioxide can be produced? Okay. How many moles of that? Remember, you can't go anywhere in a balanced equation unless you're moles. Grams won't do it, milliliters won't do it, concentrations won't do it. It's got to be moles. So 7.2 grams of oxygen is how many moles of oxygen? 32.00 is the molar mass of diatomic oxygen. So 32 into 7.2 is 0.225. 0.225 moles of oxygen. How many moles of sulfur trioxide is that? We need another conversion factor. Oxygen, sulfur trioxide. Oxygen is 3, sulfur trioxide is 2. So 2/3 of that value is 0.15. 0.150 moles of sulfur trioxide, which is right there. Yeah, they're right. That's only 2 significant figures. So I'm limited to 2 here. All right, 81, 82. Consider the following unbalanced equation. How many moles of water are needed to react with 206 grams of Al4C3, aluminum carbide? Okay, so they say it's an unbalanced equation. We need a balanced equation. Al4C3 plus water yields AlOH3, aluminum hydroxide, and methane. Okay. And we're given 206 grams of this, and we're asked how many moles of water are needed. Okay. So we need a balanced equation first. There are no unattached elements that we can use to balance later. So you set up yourself a budget. I'm looking to see, yeah, we're probably going to need to do the budget. So we have aluminum, carbon, hydrogen, oxygen. On this side, we have 4 aluminums, 3 carbons, 2 hydrogens, 1 oxygen. That's 4, 5, 6, 7, 8, 9, 10. 3, 7, 10. That's good. Over on this side, we have 1 aluminum, we have 1 carbon, we have 3 plus 4 is 7 hydrogen, and 3 oxygens. Right? So we have 6, 7, 8, 12, 10, 12. Okay, so now we can balance the equation. So where do we start? Well, if we don't have a clear idea of where to go, I just start at the top. So we need 4 aluminums, right? 4 aluminums. So that's 4 here. Now that changes. 3 times 4 is 12 oxygens on this side. Okay. It also says we have 12 hydrogens here and 4 here, which is 16 hydrogens. Okay. How about carbon? Well, we have 3 carbons over here. What if we have 3 carbons over here? That. 3 carbons. Now we have changed the hydrogens again. So 12 hydrogens here, and 4 times 3 is 12 here. So we have 24 hydrogens. Okay. 3 carbons, 24 hydrogens. Yep, okay. 4, 3, 44. Okay, we need, notice, it might not be obvious, but what's the ratio of hydrogen to oxygen here? 2 to 1. 2 to 1. 24 to 12 is 2 to 1. 2 to 1. If we multiply 12 here, that gives us 24 hydrogens and 12 oxygens. Now we're balanced. Now we can go ahead with the rest of the problem. All right. So we want to convert, we want to change this number of moles to that number of moles. So we need 206 grams, and we need a molar mass for that compound, aluminum carbide. Okay. So 4 aluminums, 26.98. So 4 times 26.98 is aluminums, and 3 carbons. $6.98. I get 143.95. 143.95 divided into 206. 1.431. 1.431 moles of Al4C3. Now we need to convert that to water. So for every one of these, we get 12 waters, which is 17.2 moles of water. Right there. Okay. That was 82. Okay. I got 15 minutes and I know I'm not going to finish. So I'll just keep rolling. 84. Consider the following reaction where X represents an unknown element. So we got 6 X's solid and 2 B2O3, 2 B2O3. That yields B4X3 and 3 XO2. Yes. Okay. If 165 grams of X, 165 grams of X reacts completely with boron trioxide, diboron trioxide, to produce 2.29 moles of this one. 2.29 moles What's the identity of X? Okay. What do we need to know to identify an element? Two choices. You either need to know the atomic number or the atomic weight, molar mass. We don't know the atomic number. There's no way to tell from this information. So we're going to look at atomic weight. What's the molar mass of X? Right? Molar mass of X is equal to mass per unit mole, right? We have the mass, 165. What we need to know, how many moles is that? Can we tell how many moles that is? Well, we've got the ratio, 2.29 moles of this, 1 to 6. Right? So B4 X3 is 1 and X is 6. So 6 times 2.29 is the number of moles. So let's say 6 enter 2.29 times 165. I get 12.01 grams per mole. How does that help us find out what X is? Go to the periodic table and just go from left to right, top to bottom, until you find the molar mass of the element that comes closest to that value. And I believe you'll find that it is carbon. All righty. Let's see, 88. Consider the reaction. Magnesium silicide plus water yields magnesium hydroxide plus silane, silicon tetrahydride, which is called silane. How many moles of excess reactant are left over if we start with 39.1 grams of each reactant? Okay, so we've got the balanced equation. Let's put that up here. Magnesium, silicon, and 4 water. I'm going to leave out the phase solid, liquid, gas, aqueous, just to save room. And silane. Okay, let's see if I got that right. Yes. Okay, how many moles excess reactant are left over if we start with 39.1 grams of each reactant? 39.1 grams. 39.1 grams. So one of them is going to run out. What we have to do is find out which one and how much is left over. So we got to convert this to moles. So 2 magnesiums, 24.31, 24.31 times 2, right? And then silicon, which is 28.09. 28.09. So we'll add those together. 24.31 times 2, that's 76.71. 76.71 grams per mole. Let's go ahead and do, well, we know what water is. Water is 18.02 grams per mole. Okay, so we got to convert these to moles. 39.1 grams and grams on the bottom, 76.71 moles. So let's divide that one into 39.1. I get 0.5097 moles of magnesium silicide. How about this one? 39.1 grams of water. 18.02 grams on the bottom, moles on the top. So 39.1 divided by 18.02 is 2.17 moles of water. Okay. So we can look at this. Normally what we would do is say, all right, convert all of this to one of these, all of this to one of those, find out which one runs out. But you can also say, if this is one, right, one of these, you need 4 times that much. So what is 4 times this? 5097. 2.04. That's equal to 2.04. So what that says is, for this amount of magnesium silicide, you need 2.04 moles of water, which means we've got more than enough. So minus 2.04, 0.13 moles of water is left over. It is excess. That's why the answer is D. Okay? That was 88. All right. 92. Fe3O4 reacts with carbon monoxide according to this equation. If 482.3 grams of carbon monoxide is reacted with excess Fe3O4, what mass of CO2 will be produced? All right, this is fairly straightforward stoichiometry. We're already told that we can use up all of the carbon monoxide because there's excess Fe3O4. So Fe3O4 plus 4 carbon monoxide yields 4 carbon dioxide plus 3 iron. This is a smelting process. If you drive carbon monoxide into this reaction at high temperature, you will have pure iron at the bottom. Okay, we're given 482.3 grams of carbon monoxide in excess here. So what mass of CO2 will be produced? What we need is to convert this to moles. Right? Carbon monoxide, 16 plus 12.01. Might as well put it in my calculator because I'm going to have to use it anyway. 16 for oxygen and 12.01 for carbon is 2801. Divide that into 482.3 is 17.22. 17.22 moles of carbon monoxide. Now we'll convert it to CO2. We don't even have to do the calculation. They're 1 to 1. 4 to 4 means you have 17.22 moles of carbon dioxide. So how about the grams? Well, let's work backwards. Like this. Moles on the bottom, grams on the top. We need the molar mass of carbon dioxide. So carbon is 12.01 and 2 oxygens is 32. 4401. times 17.22 is 75.8. Wait a minute. Four significant figures. 757.8. 757.8 grams of carbon dioxide. Right there. Okay. 92. All right. 94. A 0.216 gram sample of sodium chloride is dissolved in enough water to make 5.20 milliliters of solution. What's the molarity? All right. Remember molarity. Moles per volume, and this has to be in liters. So we need to know how many moles is 0.216 grams. 0.216 grams of sodium chloride. And we're given the molar mass right there in the problem, 58.44. Right? So we'll divide that into 0.216. Which is 3.696 times 10 to the minus 3 moles. So now we can calculate the molarity. 3.696 times 10 to the minus 3 moles. Except for one little problem. 5.20 milliliters. We need liters. So how do I do that? 5.20 milliliters. Well, what I do is I take this right here. That little m, what does that little m mean? It means 1,000th of 10 to the minus 3. So that would be 5.20 times 10 to the minus 3 liters. Okay, so now I need 5.2. And that's 0.7108. Let's see. 3 significant figures. Round it off. Molar. Right there. Okay. $94. $95. For the titration of sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide would be required to react with 1.5 liters of 0.5 molar sulfuric acid to reach the endpoint? You can approach this one 2 different ways. With titrations, if you know the normality of both solutions, then you can make a direct comparison. Otherwise, you need a balanced equation. And I like the balanced equation myself because I don't use normality that often. So it's not second nature to me. So I say, if we're going to titrate sulfuric acid with sodium hydroxide, we know what we're going to get from that reaction. It's a double replacement reaction, sodium and sulfate. That has to be 2 of them because sulfate is a 2- charge, sodium's a 1+. Plus water. Okay. Now we need to balance the equation. Right? If there are 2 sodiums over here, I need 2 sodiums there. But that gives me 2 hydroxyls and 2 hydrogens. Right? So a hydrogen plus a hydroxyl is what? Water. 1 hydroxyl, 1 hydrogen is 1 water. 2 hydroxyls and 2 hydrogens are 2 waters. Okay. Now we're balanced. Now we can do our stoichiometry. 1.5 liters of 0.5 molar sulfuric acid. 1.5 liters of 0.5 molar. So, how many moles of sulfuric acid is that? Right? Molarity times volume equals moles. So that's 0.75 moles of H2SO4. But for every one of these, you have two of those. Right? So for every, so what you have here is, if that's one of those, then you've got two of these. Does that answer the question? How many moles of sodium hydroxide? Yeah. 1.5 moles of sodium hydroxide. Because of the ratio 2 to 1. Here's your 1, there's your 2. 1.50 moles. Okay. 96. Which of the following statements is false? Oxidation and reduction. Let's see. Is A true? Cannot occur independently of each other. That's true. They never occur separately. If you have an oxidation, there's always something else being reduced at the same time. So A is true. How about B? Accompany all chemical reactions. Is that true? Every chemical reaction is oxidation reduction? I don't think so. No, it's not. Describe the loss. This describes the loss and gain of electrons, respectively. Oxidation is loss. Reduction is gain. That's true. Oxidation and reduction result in a change in the oxidation state of the elements involved. That's true. Oxidation state always changes in one of these reactions. And E always happens when an alkaline metal and a halogen react. Let's take an example. Say we're going to do sodium metal and chlorine gas. What do we get? Sodium chloride. 0, 0, plus 1, minus 1. Actually, we need 2 here and 2 here. But the oxidation states always change when you react an alkaline metal with a halogen, every time. So E is also true. The only one that's false is B, right here. All right, 96, 97. You have 3 liters of 3 molar solution sodium chloride. That's called solution A. You also have 2 liters of 1.84 molar silver nitrate. Call that solution B. You mix those solutions together. Calculate the concentration of nitrate ions in solution C. All right, so let's see what's happening. Sodium chloride solution. And we're adding to that silver nitrate solution. Okay. And that yields silver chloride solid plus sodium nitrate in solution. Okay, that's your balanced equation. What are we given? 3 liters of 3 molar sodium chloride. 3 liters of 3 molar. And silver nitrate is 2 liters of 1.84 molar. 2 liters of 1.84 molar. Okay, now we're going to put them together and we want to know what's the concentration of nitrate in that final solution. Notice nitrate is a spectator. Nitrate is on that side And it hadn't changed on that side. So you have the same moles of nitrate at the end as you started. Only what's changed? The volume has changed. So if we want to know the concentration of nitrate, we need to know the new volume. So how many moles of nitrate do you start with? Well, 1 to 1. So 2 liters times 1.84 molar is, let's see, 3.68 moles. Is that right? 2. Yeah. That's moles of silver nitrate, which is also 3.68 moles of nitrate. Okay. Now, what's the final volume? Because moles per volume is molarity. What's the final volume? Well, 3 liters plus 2 liters is 5 liters. That's the final volume. So 3.68 divided by 5. I bet we can reason this one out without even calculating. Right? 3 divided by 5 is less than 1, right? Okay. So if anything's greater than 1, cross it out. Right? Can't be that one. Can't be that one. Obviously not that one, because we've decided that nitrate is still there. And it can't be that one. So C, by process of elimination, C is the only possibility. 0.736. That's about 3/4. That's about right. Rough estimation. That's 97. All right. 99. I better scroll this one. I'm going to do this with a mouse. There we go. 99. Starting to get a little faint. Which statement is true of the following reaction? You have this reaction, 2 potassiums plus copper 2 chloride yields 2 potassium chloride plus copper. All right. Which one of these is true? Potassium is oxidized. Well, in order to tell oxidation reduction, we know it's an oxidation reduction, correct? Element in a compound. That's definitely oxidation reduction. But to answer the question, we need to know which one is which. This one is a 0 oxidation state, that was a 0. This one's a -1, that one's a -1, this one's a +1, and this one is -2. Okay? So potassium has lost an electron. Potassium is oxidized. Oxidation is loss. A is true. B can't be true. Can't have both of them true at the same time. How about C? So A is true. B is false. C, copper is reduced. 2 minus to 0. Oh, I'm sorry. Copper is 2 plus. I don't know what possessed me to put a negative charge on a metal. Copper is 2 plus. So 2 plus to 0 is, yes, it has picked up electrons. So C is true. Copper can't be oxidized and reduced at the same time. Not in this reaction. So 2 of the above are true. E is true. All right. 102, let's see if I can do this. Go over here. There we go. 102. In which of the following does nitrogen have an oxidation state of +5? All right, so in this case, we need to run down the list and find the one where nitrogen has an oxidation state of +5. So our choices are HNO3, NO2, N2O, ammonium chloride, and sodium nitrite. Okay. So oxidation state. Oxygen is always -2. Hydrogen's +1. So that means we have -6 and then a +1 equals -5. That has to be balanced by +5 on nitrogen. We found our answer. It's this one. Now, if you find a problem that has a different value for the oxidation state, then you got to do the rest of it. So this one's -2, which means a -4 total, that's a +4. This one's a -2, that means this one has to be a +2, but each one is a +1, because there are two of them. This one is a -1, a +1, so that's a +4, and a -1 is a +3. That means this one is a -3. This one is a -2, -4. This one's a +1, which means together they're -3. This one's a +3. Okay, so you got each of them identified here, 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 there, and there. Right. In case the question comes up, this is not +4, say it's I don't know, +1, then you can find it. Uh, 103. All right, that's getting a little faint. I need another marker. Let's see if this one's working. 103. Okay, which of the following is true for a galvanic cell based on the following reaction? Zinc plus copper 2 plus yields zinc 2 plus. That's copper. That's a 0. That's a 0 oxidation state, and those are charges. Okay, let's see which one of these is true. A. Zinc is being reduced. Zinc is going from 0 to 2 plus. It's being oxidized. That's false. Zinc serves as the cathode. What happens at the cathode? Reduction. Right? Zinc cannot serve as a cathode because it's being oxidized. That's false. Copper 2 plus is being reduced. Yes, 2 plus to 0 means we've added 2 electrons. So this one is true. Copper serves as the anode. Anode is the site of oxidation. Okay. So D is false. That means E is false also because you can't have 2 when there's only 1. All right, so C is the answer. Right here, that's the only one that's true out of all those statements. $105. Okay, I'm going to have to get down here and there we go. 105. The total mass of a solution is 184.8 grams. 184.8 grams total mass. The solvent mass is 125.2 grams. This is total. Mass of the solvent equals 125.2 grams. What's the mass percent of the solute? Do we have enough information? Mass percent? You need to know the mass of the solute and divide it by the total mass to find out its mass percent. So this is equal to 184 minus 125. Which is 59.6. Now we can do mass percent. 59.6 divided by 184.8 times 100. Is 32.3 mass percent. Right there. Okay. Let's see, who's next? 106. Which of the following statements is true of electrolysis? So what is electrolysis? Well, when you set up a galvanic cell, it's going to run spontaneously in one direction. Electrolysis is a process where you match and then exceed the voltage of that galvanic cell in the reverse direction. You drive the reaction backwards. It's not spontaneous. So that's the basic difference between the two, galvanic cell and electrolytic cell, is galvanic is spontaneous, electrolytic is not spontaneous. So with that knowledge, let's see which one of these is true. All right. Electrolysis is a process where electrical energy is used to produce a chemical change. That's true. You're using external voltage to drive a reaction backwards, and that produces a chemical change. A is true. Electrolysis involves forcing a current through a cell to produce a change that would otherwise not occur. That's another way of saying it's not spontaneous. The electrolysis of water produces hydrogen gas and oxygen gas. Yes, I showed you that in class as an example. If you drive a direct current through water, then you'll produce hydrogen gas and oxygen gas from the process of electrolysis. Electrolysis is used to recharge lead storage battery. That's right. The lead storage battery under the hood of your car, if you have a gasoline engine or a diesel engine, that battery, when it discharges, delivers a voltage to your system. And then when the motor starts, the alternator runs a voltage in reverse and drives the reaction backwards in your battery. That's an electrolytic process. So all of these are true. Every statement in this question, but every answer is true. Okay, 107. What's the oxidation state of ClO3? ClO3 minus. What's the oxidation state of chlorine? Remember, if you have a compound or an ion where you have rules that tell you the oxidation state of various members of that compound, then you can deduce the other one. In this case, we know that oxygen is -2. Oxygen is always -2 unless it's a peroxide. This one is -2, which means 6 total, and we hold out 1 to preserve that minus. That means this one has to be +5 for chlorine. Okay? 108. The oxidation state of oxygen in O2 is what? This is sort of a trick question, just to see if you remember all elements in their most common state at standard temperature and pressure, the oxidation state is 0. So O2 is standard for oxygen at 1 atmosphere pressure and 25 degrees. Now, 0 or 25 degrees doesn't matter. They're both the same. In this, to answer this question, so oxygen is 0. All right, 109, let's see. We need to scroll just a hair. Ooh, too far. Let's keep going. There we go. We'll stop there. 109. Oxidation state of sulfur in K2SO4. Remember, when we add up all the oxidation states, they have to be 0 in this neutral compound. So what do we know? Alkali metals are always +1. So that means we have +2 for that one. Oxygen's -2, so 4 times -2 is -8, which means together it's -6. So that one sulfur has to balance that -6 with a +6. Right. Okay, 110. When the following reaction is balanced in acidic solution, the coefficient of water is what? Is this a valid question? If we balance this equation in acidic solution, is it going to have water as a term? Well, yeah, because there's an oxygen there. Remember, the way we balance oxygens is with water. So now we have to go to our half reaction method. ClO3 minus plus Fe2 plus chloride and Fe3 plus. All right, so which one's the oxidation step and which one's the reduction? Oxidation is obvious. 2 plus to 3 plus. So this one is the oxidation step. Reduction step has to be this one and this one. So let's go ahead and calculate that oxidation number for chlorine so we can tell how many electrons are being transferred. Right? This is 3 times 2 minus is 6 minus, and we have to hold 1 out. So that's +5. Okay. Now, what's next? We balance everything but oxygen and hydrogen. These are already good. These are already good, 1 and 1. Now you balance the oxygens with water. So 3 oxygens on this side means we need 3 waters on that side. But we've added 6 hydrogens. So we need 6 hydrogens on this side. Now we can balance we can add in the electrons. So if this is oxidation, that means 1 electron from 2 plus to 3 plus, 1 electron. On this side, reduction, we have to add electrons. So how many? Well, +5 to 0 is 5 electrons. And then 0 to -1 is another electron. So there are actually 6 electrons that had to be added to get to that point. Now, in the interest of time, do we need to finish this out? In order to get 6 electrons up here, we multiply this times 6. And then we bring it down. But is that going to change water? No, not at all. So we've got the amount of water here without finishing the whole procedure. Now, if another question is asked, like, what is the coefficient of some other member, then you would bring it all down. And maybe we ought to do that. So we have ClO3 minus plus 6 Fe2 plus 6 hydrogens, and electrons are gone, chloride, and Fe3 plus, and 3 water. So there's your balanced equation in acidic solution. You know what? I can see the faint right here, Fe3 plus. That should have been 6. All right, 111. The Hall process for making aluminum involves what? Remember, what Hall succeeded in doing was using electrolysis to reduce aluminum from bauxite ore. Right? Bauxite ore is aluminum oxide. The problem he had was it has to be in solution. I mean, it has to be free ions. You had to melt it. If you put it in solution, that wouldn't work, because if you passed charge through a solution of aluminum oxide, it would just electrolyze the water, right? And the aluminum oxide wouldn't be touched. So you had to melt the aluminum oxide. Well, that happens at a very high temperature. The number I've escapes me for the moment. But I do know that one way to reduce the temperature is to alloy it with this right here, cryolite. So we're not going to make an aqueous solution. We're not going to chemically react aluminum with carbon, although in the past that was one way to do it. But Hall chose a different route. And what Hall did was he electrolyzed molten aluminum oxide and cryolite. And he did that because the melting point was much, much lower. Didn't take as much heat to get it melted. So C is the answer to 111. Let's see here. Let's go down here and scroll a bit more. There we go. 112. How many electrons are transferred in the balanced reaction? So this is a balanced equation. A balanced redox equation right here. How many electrons are transferred? All right, so let's write the equation. ClO3 minus plus 12 hydrogens plus 10 iodines, 5 and plus 6 water. Right. All right. How many electrons are transferred? Well, let's see. We determined this one earlier, didn't we? This is plus 5. hydrogen and oxygen are not oxidized or reduced. Iodine is a -1. This iodine is 0, and that chlorine is 0. So which way are we going here? Well, if we go from +5 here to 0 here, right, that is gain of 5 electrons per chlorine times 2 chlorines equals 10 electrons. Right? That should be our answer. But let's look at the oxidizing side. Right? From iodine here to here is 1 electron added, gain, 1 electron lost. Loss, 1 electron per iodine times 2, times 2 times 5 is 10, 10 times 10 equals 10 electrons. So we confirmed that the number gained is the number lost, and that's 10 electrons. Right here. Okay? (113). When the equation for the following reaction in basic solution is balanced, what's the coefficient of hydroxide? Okay, so we got to go a whole 9 yards with this one. We start off with the MnO4 minus. Let's put it way up here. MnO4 minus plus Cn minus yields MnO2 plus CnO minus. Okay. So what's going to be reduced and what's going to be oxidized? Well, the manganese is easy. Right? This oxygen is -2 times 8 is 4 times -8, -7 because we're holding 1 out. So this is +7. Well, that's that manganese. How about this manganese? This is -4 total, so this has to be +4. Okay. So we know that manganese has been reduced. We've added electrons to go from a +7 to a +4. So the reduction step is this one yields that one. I'm going to put the oxidation numbers in here so I don't lose them. So that means the oxidation step has to be this one goes to this one. Okay. All right. We know that we're going to have to add oxygen here. Right? But which one of these is actually being oxidized and which one's being reduced? Excuse me. Which one of these is oxidized? Nitrogen or carbon? That's a tricky question. And if you have to make a choice on the periodic table, the one to the right is the more stable one. So nitrogen is to the right of carbon, which means it won't change. Not for our bookkeeping scheme. So what is nitrogen in the periodic table? Well, it's 3 over from fluorine, right? Halogens, chalcogens, pnictogens. Pnictogens are -3. So this is a -3. We have to hold 1 out. So this one has to be a +2. This one's a -2. This one's a -3, which is -5, but we're holding 1 here, so -4. This is a +4. So carbon goes from +2 to +4. Which means it was oxidized. Here we go. Okay, now that we've established all the players, let's balance. Manganese, manganese, 1 and 1, good. Carbon, carbon, good. Nitrogen, nitrogen, good. Oxygen, plus water. 1 oxygen, 1 oxygen. 2 hydrogens. notice to get to the basic balancing scheme, we're going through the acid first. Right? This is my fake acid method. So we're faking it out by calling it acid first. Then we're going to resolve at the end from acid to basic solution. Okay, so that takes care of the oxygens, hydrogens. Here we've got 4 oxygens and only 2 here. Right? So we need 2 more oxygens. But now we've got 4 hydrogens. Okay. Now we can go to electrons. To go from this manganese to that manganese, we had to add, because we're reducing, 3 electrons. And to go from +2 to +4, we had to lose 2 electrons. Right? That's what oxidation means. Now we've got to balance the electrons. 2 to 3 cross multiply. Right? So we need 3 here and 2 there. So now we're going to get 2MnO4 minus plus 8 hydrogens plus 6 electrons yields 2MnO2 plus 4 water. Okay. And here we get 3 Cn minus plus 3 water and 3 CnO minus 6 hydrogens and 6 electrons. Okay, so now we're going to take that one and combine them. But before we do, the whole purpose of that last step was to balance the electrons. So the electrons are gone, right? How about the hydrogens? Well, we got 8 on this side, we got 6 on this side. Let's start bringing things down. Now let's put them in the same order. 2MnO4, 2MnO4 minus, right? Takes care of that one. And then 3 Cn minus, and then hydrogens. So we've got 8 on this side and 2 on that and 6 on this side. That means those 6 are gone, and that leaves us with 2 here. So we're going to have 2 hydrogens on this side. Okay. So it takes care of that. Now we got water. 3 waters on this side and 4 waters on that side. So no waters remain on this side. And we got only 1 water on that side. So now we have 2 MnO2, that one. We have 3 CnO minus, that one. Then we have a 1 water, right? And no hydrogens, because we already got rid of the hydrogen. Okay, now we're going to convert to basic. So in order to do that, we need to add hydroxyls here and hydroxyls here. This makes it 2 waters and 1 water. So that water goes away, and now we only got 1 water on this side. Right, so what's the question? What's the coefficient of OH minus? OH minus is 2. Right here. Okay? We can bring them all down. Right? If you needed to know something else, but that answers the question. Okay, now we're just going to simply balance equations. I got a couple of those and then we're done. All right, so we'll be probably about an hour over. Instead of a 2-hour class, it's a 3-hour class. Is it 2 hours? 2 hours twice a week? Yeah. Okay, so this one I've selected, 115. Right, there's the answer, but you have to read this. Write the balanced equation for the double replacement reaction of lead 2 nitrate and potassium chromate. Kind of got chopped off at the end. Lead 2 nitrate. Lead 2 plus, right? Nitrate, which means we need 2 of these. And then with what? Potassium chromate, right? Potassium chromate. Chromate is a polyatomic ion. Just look it up in your table. It'll be there for you in useful information. Chromate is Cr2O4 with a minus 2 charge. Minus 2, so we need 2 of those. And that's aqueous. Now, what is that going to give us? It's a double replacement. The problem tells you it's a double replacement, which means this one swaps places with that one. So potassium pairs up with nitrate, which is aqueous, and then lead pairs up with chromate. Yeah. So this one's, and this is not an oxidation reduction. This is 2 plus, that's 2 plus. This is 2 minus, that's 2 minus, that's it. But if you look it up in the chart, you'll find that this is a solid. All right, now we need to balance it. You can set up your budget, but these are usually fairly well-behaved reactions, the double replacements. You got 1 lead, 1 lead. You got 2 nitrates, so we need 2 nitrates right there. But we also need 2 potassiums right there. And 1 chromate, we're done. That's it. So 1 lead 2 nitrate, 1 potassium chromate yields 1 solid lead chromate. And in these reactions, the phase indicator is essential. This is aqueous, that's aqueous, this is solid, it's a precipitate, and that one is aqueous. Without those symbols, the reaction is incomplete. Why? Because the reaction is driven by the formation of that solid. If you don't show that solid, then you're not indicating the driving force of the reaction. Okay, that was 115. I think I got one more I want to look at as an example. Okay. Here. 124. Write the balanced equation for the reaction of aluminum oxide. Aluminum oxide. So this is a 2 minus, this is a plus 3. That means this is 3 and then it's 2. Plus carbon monoxide. That's a gas, this is a solid. And what does that yield? Actually, it tells you what it yields, right? We don't expect you to remember this one. You get aluminum metal and carbon dioxide. So aluminum metal and carbon dioxide gas. Now we can balance it. Okay, so we got that aluminum, we're going to leave it to last. We've got, excuse me, I shouldn't have done that. If we've got 3 oxygens here and 1 there, that means we need 4 oxygens on this side, right? That means, 3, 4, 1 carbon. Oh, now we need 2 carbons. But if we say 2 carbons on this side, that means now we have 5 oxygens, right? So that's not going to work. Okay, I need to do the budget in this case. So let's say aluminum oxygen, carbon. 2 aluminums, 4 oxygens, 1 carbon. It's 5, 6, 7, 2, 3, 4, 5, 6, 7. 1 aluminum, 2 oxygens, and 1 carbon. Okay, the buggeroo in this one seems to be the split of oxygens between that one and that. So if we went ahead and said 2 aluminums, that might work, and it might not. I tend to hold aluminums till last. So let's look at the oxygens again. So if we got 4 oxygens on this side, 2 on that side, if we put a 2 here, that gives us 4 oxygens. But it also gives us 2 carbons, which messes up our oxygens on this side. So what if we said 2 here, that makes 4 oxygens. That's okay. But now we got 2 carbons. So let's iterate. How about that? If we put 2 here, that makes 2 carbons and 4 oxygens, which balances the oxygens. But now we got to do the carbons. So if we did a 2 carbons here, that would mean 2 plus 3 is 5 oxygens and 2 carbons. So now let's go over here and make this one 3. Right, we're iterating. That's 6 oxygens. Right? And 3 carbons. So if we make 3 carbons here, right, like that, that makes 3 and 3 is 6 oxygens. Okay, so now we're good. All we have to do is fix the aluminum. Okay. So now we have a balanced equation. Al2O3, 3 carbon monoxide, 2 aluminums, and 3 carbon dioxide. That took a little doing, and the budget was essential to getting this one right. All right, do we have any more? That's it. So all this other stuff you see in the review document will be available for the final exam. And the final exam, just to repeat myself, the final exam nominally for the school is on Thursday. But if you're going to take it, if you show up in class, yeah, come to class, take it in class. If you're going to do it online, I'll give you till Saturday because the system grades it for me. Well, except for maybe balanced equations, I'll have to go in and fix those, but that's nothing too difficult. And it won't delay my reporting your grades the following Monday, which is when they're due. And then be sure to learn how to work the problems. Don't just memorize answers, because the final exam may have problems that look like those, but have different parameters, and you're going to come out with the wrong answer. Actually, you have to work it to get the right answer. And the other thing that I may not have mentioned at the very beginning is I'm in the process of creating a review document for this, worked problems for the review document. And I'll post that hopefully sometime this evening. If not, certainly no later than Friday evening. But that'll give you how I did it, like I've been doing with all the other chapter exams. Okay, since I'm the only one left, that's the end of our review, and we'll see you either next Thursday, not on Tuesday. Right, there won't be any class on Tuesday because that's final exam week. Thursday in class, I'll be here and zoomed in case you need help. And then that'll be the end of the semester. So get all your homework done if you haven't already done it. Be sure and get your homework in. And if you haven't gotten your last exam finished, be sure and get that one in. And then this final will be it. And I'll report your grades in Brightspace as soon as I can.